Good morning, everybody. Yesterday, we looked at black box testing and we looked at two techniques, equivalence partitioning and boundary value testing. And for both these techniques, we saw that as far as single variable is concerned, it's straightforward. And when the number of variables are n, we also did see that how to handle that case for defining the equivalence partitions and the boundary values. Now today let's look at another black box testing technique, which is the decision table testing. The technique decision table, and today we'll look at some other techniques. These come under combinatorial testing. These are black box test techniques, and the main motivation here is that program is the behavior of the program is affected by many factors. For example, the program behavior depends on what is the values of the input parameters. If there is a configuration parameter setting, it will also depend on what configuration has been set. If there are state variables which are set based on the input parameters, then it will also, the behavior will depend on what state the system is. And in many non-trivial systems, the combination of these, the number of input parameters, the number of configuration parameters and state variables becomes very large. So if we try to develop equivalence partitions and boundary value analysis, we can end up getting millions or billions of test cases, which would be impossible to test using any technique. Because as we were saying yesterday also, that you might argue that why not use some automated technique for this kind of thing. The automated technique, as we will see when we discuss about automated testing, is that even if we through some algorithm define the test cases, let's say we identify the equivalence partitions, boundary values and so on, some sophisticated algorithm, but when we run it, how do we know that the result is correct or not? That's called as an oracle, which can decide whether the result is correct or not, and so far it has proved to be a very hard problem. That is discussion for tomorrow about automated testing. But right now we'll just say that when we have large number of combinations possible for input parameters, configuration parameters, state variables, etc., we might get millions of test cases. We will see some examples today, and you can test exhaustively. And in these situations, we try to define certain combinations which define our test cases, and these become manageable number. Let's look at these techniques. So the first technique we see today is the decision table based testing. I hope everybody knows about a decision table. It's a very popular technique used in many situations in computer science and elsewhere. The main thing here is that we have the conditions here. The first rows that are green are the conditions, and then we try to find out all possible combinations of conditions, and based on the conditions we try to find out what would be the action of the system. So the conditions are typically the inputs, or maybe state variables, or maybe configuration parameters, and for specific combinations we try to find out what are the actions of the system. The actions are shown in the red here. So the top part of the table are the conditions and the bottom part are the actions, and every combination of condition, unique combination of condition, is called as a rule. So In a decision table based testing, each rule becomes a test case. So we set these combinations of conditions and check whether these actions do take place. For example, we might have a simple example can be that we have a decision C1 and C2 or C3 then A1. So we'll have if C1 and C2 is true, then C3 is don't care. If C1 and C2 is false, then C3 has to be true. So those are the two rules under which A1 will take place. So let's see how to construct this table. So here, as I was mentioning, we have these conditions we have to list out at the top, and then the actions at the bottom rows, and then for each condition we find out all possible combinations of these different conditions, meaningful combinations. There may be combinations which are impossible. We don't have to consider those. Let's see the first example about a decision table, example decision table. So the problem here is that we want to check based on three parameters that are input here, A, B, C, to a program, whether representing the sides of a triangle, whether it is not a triangle, it is a scalene, it is isosceles, equilateral, or it's impossible. So we'll form the conditions here: A equal to B, A equal to C, B equal to C, etc. And then we write the rules here and the corresponding actions here. So this is just a trivial example. So let's look at more realistic examples. Okay, and once we form this table, we will form test cases. We will give sample values for these conditions, and then we will say that these actions should take place. So we just write here that the value 4, 1, 2, A, B, C, we can write in terms of A, B, C, that is 4, 1, 2, not a triangle. If it is some illegal characters or non-numerical, we will say impossible. So these will form our test cases, decision table based test cases, DT1, DT2, etc. So this is a more complete decision table for the triangle problem. So we can form the conditions: A is less than B plus C, or B is less than A plus C, C is A plus, C is less than A plus B. If any of them is false, we will have not a triangle. And only when these are true, then we examine if A equal to B, A equal to C, B equal to C, and write the corresponding output, scalene, isosceles, or equilateral, or impossible. And then having done that, we write in terms of the input variables A, B, C. So we write in terms of the input variables A, B, C, and then the expected output. And each of these becomes a test case. So once we have a decision table, having the test cases is rather trivial. Now let's look at another example. This is about a printer troubleshooting application. So based on what is the observed symptom of a printer not working, we can write what actions we should take. This may be part of a maintenance manual or something. So let's say the printer does not print, the red light is flashing, printer is unrecognized, then we have to take these three actions. If the printer does not print, red light is flashing, but the printer is recognized by the computer, then do these two actions, and so on. So the conditions are the symptoms observed about the printer, and what action we need to take to maintain the printer. So this is another example of a decision table. Now please try to develop a decision table for this example. So we have a bank that accepts deposits on the following conditions. So the conditions put forward by the bank is that the interest rate will depend on duration, amount and whether senior citizen or not. If the duration is less than 6 months, then get 4% interest. If it is between 6 months and less than 1 year, then get 5% interest. If it is between 1 year and less than 2 years, get 6% interest. If it is 2 years and above, get 7% interest. And also the interest rate depends on the amount you deposit. If you deposit amount is excess of 1 lakh and less than 10 lakh, then you get 1% extra for each slab of duration. And in addition, if it is a senior citizen, you get 1% extra for each slab. So how do we develop the test cases for this? To develop the test cases, we have to first do the decision table. So please try to draw the decision table for this. I will display the solution so that you can check out. So as we said, the decision table, the top rows are the conditions and the bottom rows are actions. And for each conditions, we have to have all possible combinations of the values that it can take. So please try this out. Please try to develop a decision table for this problem, and if you are able to develop the decision table, then generating test cases is almost mechanical. So I'll just wait for a few seconds. Please try if not the complete decision table, because we don't have that much time to really wait for you to do the decision table. Just wait for a few seconds so that you can quickly try out at least the skeleton of this decision table. Okay, so let me just display the solution so that you can check out whether you are able to draw the decision table, because the crux of this decision table based testing is to develop the decision table. And of course, as we will see that the cause effect graphing, that is another way we can represent the decision making, and finally there also the finally we will have to convert the cause effect graph into a decision table. So the decision table based testing is the foundation, or is the main thing in cause effect graphing. So let me just look at the solution. I hope you have tried out. If not, please try, because unless we try out, we will not appreciate what is involved here. Achha. So I have not really put the solution here. Let me just draw it on paper. Let me draw the schematic of the solution on paper. So please observe that there are actually 3 conditions which are explicitly mentioned for our to make it easy to realize. This is the first problem, so it's easy here. So there is we draw the table, and at the top rows of the table we write duration, amount, and whether senior citizen or not. And the senior citizen is either yes, all these will become yes or no. So based on senior citizen or no, we'll have look at the possible conditions for the duration and the amount. And the amount can be greater than 1 lakh. So all these will become greater than 1 lakh, and this will be between 1 lakh and 10 lakh. You can also do this as the conditions you can form here is that whether the amount is 1 lakh, whether the amount is less than 10 lakh, etc. That's another way you can form the decision table, but they are equivalent. So here the decision is based on the values here. So all the rows here will have amount less than 1 lakh, and here it is between 10 lakh and 1 lakh and 10 lakh. Similarly, here when it is not a senior citizen, we will also have amount greater than 1 lakh, sorry, amount, okay, we should have, there are three things, right? Amount is less than 1 lakh we should also have. So there are three conditions here. Amount is less than 1 lakh, greater than 1 lakh, but less than 10 lakh and greater than 1 lakh and less than 10 lakh. Okay, more than 10 lakh. So amount is less than 1 lakh, between 1 lakh and 10 lakh and greater than 10 lakh. So these are the three possible variations of the amount based on which the outcome will vary. Similarly here also, the senior citizen, no, will also have all these three combinations of conditions between 1 lakh and 10 lakh and greater than 10 lakh. Now for each of these 1 lakh to 10 lakh and greater than 10 lakh, we will have all possible durations. So duration less than 6 months, between 6 months and 1 year, 6 months and 1 year, between 1 year and 2 year, etc. And for each of these we write down all combinations of the durations. So totally how many rows do we have here? Can anybody write on the chat box how many rows we'll have for this decision table? So these are the conditions and these are the actions. The action will be the output, what will be the interest rate. So can anybody determine what will be the number of rows or rules or the number of test cases for this problem? Just waiting for anybody to respond that what will be the number of test cases for this case. So I'm not getting any response. So please think about it and let me know as we proceed. We won't wait for you to write because it's taking time for getting the response. Please find out what will be the number of test cases for this problem or the number of rules here. I've just given the schematic of the solution. It takes senior citizen, yes and no, and for each of these we consider the possible variations of the amount, that is 3 of these, and then the duration, that is 4 of these. Now there is a quiz here. Develop black box test cases. So the black box test case here, just see that these are the conditions here, and we need to develop the decision table based testing. So this is the description of the policy for charging customers for certain in-flight services. If the flight is more than half full, then meals are served. And if the ticket cost of the flight is more than 3,000, then the meals are free. Unless of course if it is a domestic flight, because on all domestic flights, if at all meals are served, they are charged. So how do we develop the decision table for this problem? Please try this. If the flight is more than half full, then only meals are served. If the ticket cost is more than 3,000, meals are free, otherwise they will be charged. And in domestic flights, the meals are always charged. If at all they are served, they are charged. So how do we develop the test cases for this? So we write a program where we input these parameters, that what is the occupancy of the flight, what is the ticket cost, whether it is a domestic or international, and then the output should be that whether meals are served or not served, and whether the meal should be charged or free. So please try this, to draw the decision table for this, so that once you develop the decision table, each rule will become a test case. So actually, since our number of hours is very restricted, we will not really have too much time here for you to try out. We'll just display the solution. Please compare with your solution, your schematic. I hope that you would have come with some scheme of solution. At the first cut, you can just write the conditions and the actions, and then the possible combinations. So whether it is more than half full, no, and yes, as you are saying that you first find out for the one that is having the lowest number of outcomes, write them no and yes, and then whether it is more than 3000 per seat, fill that out, all possible combinations here, and then and the domestic flight or not, just write down. So we have 8 combinations. So that many test cases trivially. But then let's see, can we do better? So once we write down the actions, we can try to optimize the number of test cases. See here that the meals are not served if it is no. So it depends only on this condition. As long as it is no, meals are not served. And also we can even optimize this. So all this we can just test out, club this. As long as this is no, meals should not be served. So we can now redraw the decision table to minimize the number of test cases. You can find out that these part are all we can club into one, these two we can club into one, because see here, as long as this is yes and this is no, then this outcome only holds, and even this one. So let's draw the optimized decision table. So as long as the flight is not more than half full, don't have to serve meals, so no here, free meal is no. And as long as this is y and this is n, only meals will be served, it will not be free. And if this is yes and this is no, then it will be free, meal will be served and it will be free. And if all are yes, then it is only meal will be served. So we need 4 test cases for this case. That's the optimized test case. So while drawing the decision table, we have to check if we have considered every condition of the conditions. So every possible values that the conditions take, we should be able to have considered that. Otherwise, some aspect of the behavior will not get tested. And we should also ensure that there is no 2 different actions for the same combination of conditions. If this is your decision table has this symptom, that for the same combination of conditions you have 2 different actions, contradictory actions, then there is something wrong with the decision table. So the decision table based testing is appropriate when there is lot of decision making. There are important logical relations among input variables, calculation involving subset of input variables, cause and effect relation between input and output. Depending on some input, some outputs are set, and there is a complex computation logic. If it is trivial, then we don't have to draw the decision table. But then we must remember that if you are manually drawing it, decision table will be hard if the number of rules become 100 or 200 or million, it becomes difficult to handle it manually. So there are a few more quizzes. Please try it out today, and if you have difficulty solving any of these, please raise the point. Next class we will solve this. So this problem is about a e-commerce site which gives following discount. The members get 10% discount for purchases lower than 2000, and if this is more than 2000, they get 15% discount. Purchase using SBI card fetches 5% extra discount. If the purchase amount of after all discount exceeds 2000, then the shipping would be free. So please find out how many test cases are needed, optimal test cases, and also which are the test cases. Please try this out. There is even one more problem for you to try out. This is about the grading of students. Between the range 80 to 100, they get they admitted, and okay, this is about admission of students. So if their mark, the previous examination is between 80 to 100, they not only get admitted, they receive a scholarship. So if their mark is 70% up to 80%, then they are admitted but no scholarship. In the range 60% to 70%, they are admitted if they have no failures in their previous examination. And if any of these conditions are not met, then they are not admitted. So please draw the decision table and find out the number of test cases and the optimal number of test cases. And as we mentioned in the beginning of our discussion, that the decision table is at the heart of the cause effect graphs. If we know decision table testing and if we are able to draw decision table, then the cause effect graphing is extremely simple. It only helps us to form the decision table effectively. Now let's look at the cause effect graphs. Here again, we are trying to explore combinations of possible inputs. The combination of inputs are called as causes, and the corresponding output are called as effects. So one advantage over decision table testing is that here the optimization is more inbuilt here. So the combinatorial explosion that is seen in a decision table can be restricted here. So here the cause and effect are represented as nodes, and also we can include constraints, and we can have introduce intermediate nodes to link between the cause and effect. We'll just discuss one problem, and if you're familiar with the decision table, then it should not be any effort at all. And again, the cause effect graph itself does not give you the test cases. We have to convert it into a decision table. Of course, it's rather more mechanical. So let's try to do the cause effect graph for this example problem. So the example problem is that if deposit amount is less than 1 lakh, then the rate of interest is 6%, 7%, 8%, depending on the duration, whether it is less than 1 year, 1 year to 3 year, or 3 year and above. And if the deposit amount is more than 1 lakh, then the rate of interest is 7%, 8%, 9% for the same durations, similar durations. Now let's do the identify the causes and the effects. So what will be the causes? The causes will be what's the amount deposit and what's the duration of the deposit. So we'll let's identify the causes. What's the duration of deposit? 1 year, less than 1 year. That we'll write it as C1. C2 is between 1 year to 3 year. C3 is greater than 3 year, and the cause 4, this is also another input, the deposit is less than 1 lakh, and cause 5, which is the deposit greater than or equal to 1 lakh. And the effects or whether the deposit rate is 6%, 7%, 8%, 9%. These are the effects. So having done this much, we have to find out which combinations of causes yield which effects. So each of these gives us the combinations of conditions. If it is less than 1 lakh and amount is duration is up to 1 year, it's 6% and so on. So the same thing we can just draw it. So C1, C2, C3, these are the duration of the deposit, and C4, C5 I've just drawn to simplify the different color. The C4, C5 are the amount of deposit, whether it is less than 1 lakh or greater than 1 lakh. Now I have given this AND symbol here, and I'm just saying that if the deposit is less than 1 year and the amount is less than 1 lakh, then the output is E4 and so on. So these combinations of conditions, I have just written a intermediate node to help simplify this diagram, because there are for certain ones this output is the same. Either I have written OR symbol here, either it is this combination or this combination, the output is E2. So the cause effect graphing is extremely easy to draw if you can identify the causes and the effects and which combinations of causes yield which effect. It's easy to draw. And once having drawn this, we can then convert this into a decision table. So we just mechanically write out what are the causes there and what are the effects, and then see whether these causes, what are the combinations of causes results in which effect. So just see here that we have not explicitly considered all possible combinations of conditions, just considered 5 of these. So the cause effect graph in a sense gives a optimal set of test cases, which decision table we might have to optimize ourselves, otherwise we will end up with getting a exponentially large number of test cases. So now let us look at a combinatorial testing. Here also there are combinations in the input. Let us look at that. So sometimes you have a large number of options. This is a word processing software, and here you have several options which you can set. For example, whether it is a strike throw, double strike throw, whether it is a small case, capital, whether it is shadow, emboss, engrave, and so on. In a typical word processing software, Microsoft Word or something, you open you try to format, set the font, you will get all these options. And just see here, not only you can set these, by clicking this you set the effect on. If you click here, the shadow is on, don't click, shadow is off, and then corresponding to that, which font. So there may be 50 fonts here, font types you can select, and you can also select which style, whether it is italic, regular, bold, bold italic, etc. And also you can select the size here. The size, there may be 50 or 60 different sizes. So if you would draw a decision table or a cause effect graphing for this, the number of test cases will be extremely high. How many test cases will be needed for this case? Assume that there are 10 of these. So some are shadowed out, we can't set it. So if you count here 4, 3, 6, okay, 9, okay, 10. Let's assume that even if it is there. So let's assume that if, okay, 6 plus 4, 10, okay, I'm sorry, 4, 3, 7, 3, 10. 10 of these we can set, either set it or don't set it. So what are the possible combinations of the conditions? 2 to the power 10. So just itself this much yields 1024 test cases. Now this you have to consider for each combination of these. Now let's assume that the number of combinations for the font type is 60. So 60 into 2 to the power 10, and let's assume there are 4 of this. So 60 into 4 into 2 to the power 10. Now let's assume there is another 50 here. So finally it will be 1024 into 60 into 50 into 4. 60 into 50 is 3000 into 4, 12,000. 12,000 into 1024, which is something like about 12 million test cases. It's too many just for testing all combinations of font setting, because unless you test a specific combination, you might be afraid that the system might crash, or it might the font might get deformed. So we need to check those conditions, but this is just too many. So how do we handle this situation when the number of conditions are too many? If the number of combinations are less, we can try our decision table testing or cause effect graphing and so on, but in this case combinations of conditions are just too many. So let's see the general principles here. Before that, let's state our assumption. The assumption is that we are not considering system state, because that will make it further complicated. We assume that as long as certain values of this input parameter are set, the system will behave similarly. Just to simplify the problem, the system has only one state. If the system has multiple states and state transitions and so on, then it becomes a further complicated problem. We need more complex thing. Now let's see a system without having any states. That's the assumption. Now here one key assumption that we make, key observation actually, that in many situations it is observed that a fault is caused by interaction among few factors. So it may be that when the font is size is 10 and the font type is times and it is shadow, then only the problem comes. So only for some combinations the problem comes, some few factor combinations the problem comes, and all possible combinations we don't have to check. So in this situation we can dramatically reduce the number of test cases. We will see that 1,000,000 may become like 10, 20 or 50, which is doable if we consider this optimization, this observation arising, the optimization arising from this observation that only the interplay of few factors cause the bug. Now let's see some examples. Okay, so before we look at this optimization of combinatorial testing, let's in the later moment look at this Dilbert cartoon on testing. Just see here, the manager comes up and says to the tester, he is the tester here, and to the tester the manager says, in the short time you have worked on quality assurance and testing, you have found a huge number of flaws in our prototype. So he thought that manager is praising him, he's found too many bugs and so on during testing. He says, that's my job. And the next statement from manager is that you are jeopardizing our schedule. The entire project will fail and it is all your fault. So he is now blaming the tester because he has found too many faults. Then he says, why is it my fault? He says, if a tree falls in the forest and we have already sold the tree, does it have quality? So he says that as long as you sell it, how does it matter if it has bugs or so? If it is sold the tree and then it already is not of quality and just there, how does it matter? So then he gets upset. The tester says, how many angels can dance on your head? So the first thing that we'll see the dramatic reductions that may be possible. Now let us assume that the number of inputs is 7 and each one can take 2 values. So each input is either true or false or 1 and 0. So what is the number of combinations of the input values? So that is 2 to the power 7, 128. So if we used decision table based testing or a cause effect graphing, we will end up with 128 test cases. But then we can try out pairwise reductions. So we just consider the possible conditions between any 2 of these. It will become clear what we mean by any 2 of these. Out of the 7 input values, we will assume possible combinations for all pairs of this. So we will not really consider 128, but we will consider pairwise. And then the number of test cases we need is 8. 13, and each value can take each input can take 3 different values. Then we will have 13 to the power 3, which is something like 1.6 into 10 to the power 6. So 1.6 million. And if we have 40 inputs and each input can take 3 values, then we will have 3 to the power 40, which is something like 1.2 and 10 to the into 10 to the power 19, that is 0.1 billion. But then if we consider pairwise, see, this becomes manageable. Here it is 8, 15 and 21. And the research results show that these ones, if we consider, they detect almost as many faults as these ones. I am not saying that they detect, they are as effective as this one. I am saying that they detect almost as much as these ones. So maybe slightly less. But then just see the effort that you would have to put here and the effort that you will have to put here. So why is it so? Let us see some examples about that. So a T-way interaction fault, we call a fault that we observe on the output as a T-way interaction fault if T of the parameters assume some specific value. So only under that values of the T parameters, the output will be faulty. And if it is a one-way fault, then the fault will occur as long as that one value, one input parameter has some value. A pairwise fault is a T-way fault where T is equal to 2. That means that a pair of conditions, certain pair of conditions, they have some value 0, 0 or 0, 1 or whatever. And experimentation had showed that in any software, a large number of faults result from simple faults, that is one-way fault and pairwise faults. So let us see some examples why it is so. First, the single mode bugs or the one-way bugs. Here, as long as one input value, one of the input value has a certain value, then the problem appears. For example, a printout always gets smeared when you choose the duplex option on the print dialog box. So only when out of the many parameters, if you somehow set the duplex option in the print dialog, then you have this severe problem. But all other parameter combinations, they don't really cause any problem. Now let us look at the double mode fault. So here, when two of the inputs have some specific value, for example, in the printer setting, the printout gets smeared only when the duplex is selected and the printer model is 394. So only when we consider these two settings, that printer is duplex and the model selected is 394, then the printout becomes smeared. There may be dozens of other parameters. So their values don't really affect as long as we have set these two. As long as these two are 1, 1, all other values don't matter. And even if this is 0, 1 or 1, 0 also, the bug does not appear. Only when this is 1, 1, the bug appears. So this is called as a double mode fault, and the experimentation shows that large majority of faults are single and double faults. Of course, the multi-mode faults are much rare. Here 3 or more input parameter setting cause the bug. Let's see one example of a pairwise fault. So we have written this C program. Okay, not a C program, it's just a pseudo code here. So somehow the programmer missed this statement. If x is equal to x2 and it takes 3 parameters, just see here x, y, z, and depending on this parameter values, if x is equal to x1 and y equal to y2, it outputs x, y, z, outputs f of x, y, z. If x is equal to x2 and y is equal to y1, it outputs g x, y. And if x is equal to x2 and y equal to y1, then it should be f x, y, z minus g x, y. So this line the programmer missed, and therefore this combination would match the default combination, which is f x, y, z plus g x, y. So even though there are 3 parameters, if we set possible values between pairs of input, like we give x is equal to x2 and y equal to y1, under that situation this bug will get exposed. So we don't have to really consider 2 to the power 3 8 cases, but we have to consider the pairwise cases, which may be 4 or something. So let's see how to go about developing these test cases. So this is another larger example with 34 on-off switches. So this is a panel, control panel in an aircraft or in any place. Many places you can find such panels where there are many settings to be done. And here also each of these can be set into many values. So if you want to test it, then there are 34 on-off switches here. So 2 to the power 34 and plus these values, these are very large number of test cases. So we can use pairwise testing here, and we can eliminate, we can detect majority of the bugs. There is another example here, Android smartphone testing. So let's say there are various parameters that can be set for an Android phone, because the Android phone works for many platforms. It can be Samsung, it can be Sony, etc. So different platforms, mobile phone hardware, they set this Android smartphone. For example, they can set either the hard keyboard hidden as no, undefined, or yes, keyboard hidden no, undefined, yes, 12 key, no key, QWERTY key or undefined, navigation hidden, navigation undefined, orientation landscape, portrait, square or undefined, screen layout size, touch screen, whether it is finger, stylus, undefined. So these are the configuration parameters for the Android phone, and just this much configuration will lead to 3 into 3 into 4 etc is 170 to 800 combinations. So if the operating system needs to be tested, the Android smartphone operating system needs to be tested, then just to test each configuration we will have to have 170 to 1800 test cases. And now under these combinations there will be several tests have to be run. Just imagine the complexity. But in a pairwise testing we might just end up with some 12 or 15 test cases. So The optimization here that we talked about is we don't have to look for all possible combinations of the input values as long as we have considered all pairwise combinations of input. So there is a quiz based on what we discussed so far. We want to design a black box test suite for a function that accepts two strings of size up to 10 characters and reports the number of times the second string occurs in the first string. So this is our last quiz on black box testing. So on all the types of testing that we have discussed, namely the equivalence class, boundary value, decision table, and the optimizations on combinatorial testing, the pairwise testing. So based on that, I just set this quiz here. We want to design black box test suite for a function that accepts two strings, size up to 10 characters, and reports the number of times the second string occurs in the first string. So how do we design the black box test suite? The first thing is, of course, the equivalence partition. And there are two parameters here, two characters. And then, as we discussed earlier, the valid and invalid, these are two broad classes. And under that, we have to consider various subclasses. So please try this out, and if we find it difficult, we'll solve it. Now let's look at the white box testing. So far we have been looking at the black box testing. Let's look at the white box test techniques. As we discussed earlier, in a black box testing we don't need the code. We just need the functional description or the specification. On the other hand, in white box testing we don't need the specification. We just need the code. So a white box testing therefore is also called as code based testing or structural testing, because we mainly use code structure of the program. And as long as the white box testing strategies, there are a large number of strategies here, dozen, 1 dozen or more than that. But we can broadly classify them into either a coverage based testing or a fault based testing. In a coverage based testing, we check whether the test cases cover certain program elements. Element can be a statement, it can be a decision, it can be a branch from one statement to another statement. So these are the elements of a program. Whether certain program elements are executed. So that is a coverage based testing. Whereas a fault based testing, here we try to see whether there are test cases which expose certain category of faults. For example, whether a int has been inadvertently made a float and so on. So the coverage based techniques, okay, this consists of both coverage and fault based techniques. So these are the coverage based techniques: statement, branch, path coverage, content coverage, MCDC, and data flow testing. These are the coverage testing, and mutation testing is an example of a fault testing. So whether a specific fault test cases have been designed to be able to detect certain specific type of faults, that is mutation testing. Now let's see that if we are doing a thorough black box testing, do we need white box testing? Or if we do a thorough white box testing, do we need a black box testing? So or in other words, do we have to do both black box and white box testing? If we do one testing thoroughly, isn't that enough? To answer that question, we have to show that some bug, at least some example bug, which can only be detected by black box testing, then we have to do black box testing. And also whether certain bugs can only be detected by white box testing. black box testing cannot detect those bugs. So then we have to do white box testing also. So please think of one example where only black box test can detect those bugs. White box cannot detect those bugs. And also another example we need where only the white box testing can detect those and black box testing cannot detect those. So the answer is here actually. So as we said, white box testing test cases are designed only by looking at the code. We don't need the specification. So whether the code has implemented all functionality in the specification, that we cannot check by white box testing. We can only check code, but whether code for some functionality has been implemented, we need to consult the specification. And whether some scenario that was mentioned there in the specification, has it under some functionality, has it been implemented? We cannot tell just by looking at the code. Similarly, just by doing the black box testing, we cannot say that whether there is a Trojan in the code. So somebody has implemented extra functionality. Just by doing black box testing, we cannot determine that. And also some code parts may not be reachable by doing black box testing. So there may be bug in some specific combination which we may not be able to detect on black box testing. That is, some statement, if it gets executed under some conditions, there will be a problem. So we already seen what's a coverage based testing and a fault based testing. So in a coverage based testing, we design test cases such that some program elements are executed, or which we also called as covered. On the other hand, in a fault based testing, we need test cases which help in discovering some type of fault. Maybe a data type of something is changed, float to int, whether statements, the programmer has interchanged some statements, whether the array is out of bound, and so on. So in a coverage based testing, we will concentrate on the statement coverage, whether all statements are executed at least one. Branch coverage, whether each branch is taken. Condition, whether each condition inside the branch condition are taken once, each condition is true at least once and false at least once, and multiple conditions, that is all combinations of conditions. Just see the difference between a condition coverage and multiple condition coverage. In condition, as long as each component condition is sometimes true and sometimes false, we are happy about that. We say that this is satisfied. But here we need all combinations of conditions. So let's say we have a composite condition or a branch condition consisting of three conditions, C1, C2, C3. So as long as you have two test cases, TTT and FFF, then all component conditions have taken all possible values. So even with two test cases, we can satisfy condition coverage. Whereas a multiple condition coverage will require 2 to the power 3, which is 8. And then we'll look at the path coverage and the dependency coverage. And then before we discuss those coverage based testing techniques, let's look at this concept of a stronger and a weaker coverage. So if the program elements covered by some test technique ensure coverage of elements achieved by some other technique, then this we call it as a weaker technique, and this we call it a stronger testing. What it implies is that if we are doing a stronger testing, we don't have to do the weaker testing. So many times you can compare to coverage based testing as which one is weaker and which one is stronger, but sometimes they may be complementary. Only some elements are common, but there are some elements which strategy 2 does not, and some elements which strategy 1 does not. So then we will have to do both the types of testing. So if we are doing this blue one, we don't have to do the red one, but this violet and blue will have to do these two types of testing because they are the complementary testing. The simplest one is the statement coverage. In statement coverage, we just ensure that our test cases, they execute every statement in the program. So as long as every statement is executed by some test case or other, we say that statement coverage is achieved. And the main idea behind statement coverage is that unless some statement is executed once, we don't know if there is a error in that statement. But then we need to also be aware that by just executing a statement once, we don't know for sure whether that statement is alright. Maybe we executed once, it worked well because some parameter was set to be something, and then if the parameter is different, then possibly it will work wrongly. So, but then the minimum requirement for testing is that statement coverage. This is the minimal testing, that every statement should at least execute once. So we don't know whether if that statement, if it executed, it will crash the system or something. So at least once we need to execute every statement. But then even if we do statement coverage, there is no guarantee that it will behave correctly for all input values. So it's a very weak testing. The other testing, it is actually the weakest of all coverage based testings. So how do we measure the coverage? We can consider how many statements have got executed by a set of test cases divided by what is the total number of statements in the program. So we might say that 80% code coverage is achieved or 90%, but then if we are doing only statement based testing, we need 100% coverage. Should not be anything less than that, unless we have unreachable code. So let's see this example. So this example is the famous Euclid's GCD algorithm, which computes GCD of two numbers just by subtraction and addition. Okay, just by subtraction here. So how many test cases will be needed for the test cases will be in terms of the values of the variables x and y. So how many test cases will be needed for achieving statement coverage for this? Okay, as long as this is true, x is not equal to y, and also x is greater than y. So let's say this is 4 and 3. So 4 is greater than y, 4 is not equal to y. So this will execute, this will execute, this will execute, and then this will execute. But what about this? So we need another test case when x is less than y. So for this example, we need 2 test cases. Okay, so this is the same problem. We can choose a test case, test set. I think 2 should be enough to test the case, but here we've taken 3. So for that specific example, as long as all the statements are executed, we should be able to achieve statement coverage, and just 2 carefully chosen values should be able to cover all the statements, will execute all the statements. Now let's look at the branch coverage testing. The branch coverage is also called as decision coverage. Here we require the test cases to achieve to set the branch condition to false and true and false for all branches, and then we are claiming that this is a stronger testing than statement coverage. So how do we show that the branch coverage is a stronger testing? Now let's take the same example. How many test cases will be needed here for branch coverage? So we need this to be set true and false. In the earlier case, we just had 2 test cases and which achieved the statement coverage. But here, how many test cases will be needed for branch coverage? So for this branch, we'll have 2, and this branch, actually one of these will be towards this also. Let's say we take 3 and 3 and 3 and 4. So 3 and 4 is already there. So 4, 3. So 3, 3, 4, 4 and 3, 3, 3, 4 and 4, 3. That will achieve branch coverage in this. So we need one extra test case compared to statement coverage. But then how do we prove? Okay, we need totally in the list about 3 test cases for branch coverage. And here we can compute the adequacy criterion, which is the total number of branch combinations that are possible, the total number of branches that are possible, and how many of those branches have been taken. So for the previous case, there are 4 branch outcomes, and then if we execute 3 of that, we will get 75% coverage. But the quiz here is that how to show that branch coverage is stronger than statement coverage. How do we show that? So can anybody suggest how do we show branch testing is a stronger testing than statement coverage? Or in other words, we will have to show that branch testing will ensure statement testing. But statement testing cannot ensure branch testing. Then we have this branch is a stronger testing than statement. So please listen again. We have to show that when we do branch testing, we will automatically have achieved all statement execution. But then all statement execution will not really result in execution of all branches. But how do we show that? So there are 2 clauses here. The first thing is whether branch coverage will guarantee statement coverage. Okay, this is the definition of stronger testing, so that we already know. Okay, we're just talking, I think I don't have the solution here written down. So let me just write down here. So to show something is a stronger testing, we need to show that branch coverage ensures statement coverage. Not only this, we will also have to show statement coverage may not cover all branches. So there are 2 parts to this proof. The first one is straightforward, because every statement will lie on some branch or other. There can be a statement which lies doesn't lie in any branch. So as long as we achieve branch coverage, statement coverage is implied. The first one is straightforward proof that every statement must belong to some branch. So as long as we achieve branch coverage, all statements will be executed. Now what about the second one? We have to show that when we have achieved statement coverage, branches may not have been covered. So for this, just by showing one counter example should be enough, that so that branch coverage is achieved, but statement coverage is achieved, but at least one branch which is not executed. So the simplest example for this may be if A greater than B, C equal to D. So here, as long as A greater than B, just one test, this will get executed. So as long as this is true, this will get executed. So statement coverage is achieved for this program, but branch coverage is not achieved. We are not tested what happens when A is less than or equal to B. So for branch coverage, we need to test with another test case. So branch coverage is a stronger testing than statement coverage. There are many tools which help us to compute coverage report. For C program, GCOV with gprofile and GCOV, those are very popular tools. For Java, there are many tools, Kubertura, Eclema, etc. We'll just have a look tomorrow, but we might get a report something like this, that the green ones is after we execute certain number of test cases, how much of the coverage is achieved for certain functions here. So as we execute more and more test cases, we will get these will become greener, and it will also show that which statements have not been executed. So what we are saying here is that as long as we are doing a branch testing, you don't have to do statement testing. That will be automatically ensured, because branch testing is a stronger test than statement testing. But if we are doing branch testing, is that enough? Is that a good testing of a program? No, not really, because if a branch consists of composite conditions, then some bugs can get missed. This is just one example bug here, that we have this condition on some decision statement, some branch. If digit high is equal to 1 or digit low equal to -1, then do some action, else do something. So just see here that as long as digit low, we take the value true here, as long as we set this as true, then the digit high equal to 1 will achieve true, and digit high equal to not equal to 1 will achieve false. So in other words, we are not checking that whether digit low is not equal to -1, will it cause a problem? So there can be some bugs which can be missed. By branch coverage, we are not checking whether some component condition takes some value. There may be some bugs when digit low is not equal to -1. So we need to do condition testing. As we said, one condition testing is the multiple condition coverage. So here each condition should be made to assume true and false, the multiple condition coverage. So if we have expression like this, C1 and C2 or C3, so we should have C1, C2, C3 should be exercised once, each outcome of C1, C2, C3. So C1, C2, C3 should be true and false. So as we said, that condition testing can be basic condition testing or multiple condition testing. So the basic condition testing, as long as some condition has achieved some true or false anytime, we are happy. We are not considered about all possible conditions, combinations of conditions. Okay, so I think the coverage that we have written is for multiple condition coverage. So in the basic condition coverage, whether all possible, yeah, that's okay. So 2 into number of basic conditions is the basic conditions testing. So if we had 2 component conditions, so 2 into 2, that is 4, and how many truth values have been taken by the basic conditions? So have all taken true and false, then this will be 100%. So if we are doing a condition testing, branch testing is implied. So condition testing is a stronger testing than branch testing. And if we keep them in a hierarchy, then statement testing is the weakest testing. A branch testing or a decision testing is stronger than statement, and the basic condition testing is stronger than the decision testing, and the multiple condition testing, where we consider all possible combinations of component conditions, that is the strongest testing. But for a multiple condition testing, the number of test cases can become extremely high. If we have n component conditions, then the number of test cases will become 2 to the power n. So if we have, let us say, 10 component conditions, which typically occurs in controller type of software, in an embedded controller or something, it's very easy to have 10 or 20 component conditions. Then we'll have 2 to the power 10, 1000 test cases for just one branch for condition coverage, and it becomes impractical. So a multiple condition coverage is practical only if n is small. But what do we do if the number of component conditions are large? So this is a multiple condition example of this code. How many test cases are needed? So we have setting all the 5 of them true and false, need 32 test cases. Of course, the compiler uses short circuit evaluation, and in that case, if we consider short circuit evaluation of this, then the number of test cases will be lower than 2 to the power 5, 32. But then when the number of component conditions are 10 or 20, multiple condition coverage becomes very difficult to achieve. And for that, to achieve bug detection as much as a multiple condition without really having an exponential number of test cases is the modified condition decision coverage, or MCDC coverage. In MCDC coverage, the number of test cases actually become linear in the number of conditions. In a multiple condition coverage, it becomes exponential in the number of conditions, 2 to the power n, or if each component condition can take 3 values, then it will be 3 to the power n. But here it will be 2 into n or something like that. So it becomes linear compared to an exponential in a multiple condition coverage. So what are the requirements for MCDC? Here we just ensure that each component condition, when it is made true or false, the entire branch outcome becomes true and false when the other component conditions are set at some value. So for that, we do, for every component condition, we check that it independently influences the output, the outcome of the decision when the other components of the conditions are held at some value. So we have just skipped the details of MCDC because those are not part of many university syllabus. The MCDC, we just skipped it. Just we defined what it is, but then if anyone is interested to really have a discussion on MCDC coverage, we can do that. For the time being, let's skip it. So if we now look at our subsumption hierarchy, statement coverage is the weakest. Slightly stronger one is the branch coverage or the decision coverage, and the basic condition coverage or the condition and decision coverage is next one, and MCDC coverage is stronger than this, and of course the strongest is the multiple condition coverage. So that's the subsumption hierarchy. Now let's look at coverage of paths. The main idea here is that if we can define the paths in a program, execution paths, then we will require test cases to execute all possible paths in the program. So if we can identify paths in the program, we can require the testing to be done such that all paths are executed, because even though branches are executed, all paths may not have been executed. So a path testing will be definitely stronger than statement testing. We would like you to really think about it and come up with a proof that path coverage is stronger than decision testing or branch testing. But how do we define path? We can just look at a program code and identify all the paths. We need to take help of a control flow graph to determine the paths in the program. A control flow graph is a representation of the program, a graphical representation of the program structure. I hope all of you know how to draw a control flow graph. But then there are some points where mistakes are typically committed. We'll just look at that, and so that given any program we can draw the control flow graph for the program. So a control flow graph we can define to be a graph which describes the sequence in which different instructions of the program get executed, or in other words, the way the control flows through the program. So how do we draw the control flow graph? Given any program, how do we draw the control flow graph? The first thing we need to do is to number all the statements, because these will become the nodes of the graph. Now we draw one node corresponding to each statement of the program, numbered statement. So statements we have numbered, and let's say 1 to 10, and we draw 10 nodes, and then we draw the edges. If there is a possibility of execution from one node to transfer to the another node, then we draw an edge between that. So if there is a possibility that control can pass from one node to another, then we draw an edge between that. Let's look at this example. So in this example, we have the same Euclid's GCD program. Now can we draw the control flow graph for this program? Actually we can draw the control flow graph for any program. Why this? Any large program also we can draw if we know the basic type of statements and how to represent them in control flow graph. So every program is actually made of three types of statement: the sequence, selection, and iteration type of statements. Okay, so this is the representation of this, but let's see what are the types of the statements and how is the representation for those. For example, they might draw an edge between 5 and 6, but there is no edge between 5 and 6, just see that. So let's see how the basic types of statements are represented in a control flow graph. Then we can, given any program, we can find the representation for the different statements, and then we will be able to draw the graph. So any program consists of three types of statements: sequence, selection, and iteration. Sequence, when one statement is executed, immediately after the other statement is executed. one subsequent statement is executed. The immediately succeeding statement is executed as soon as the first one completes. So that is simple. You just draw these two nodes, 1, 2, and then draw an edge. Sequence is easy to draw. Nobody makes a mistake usually in the sequence statement. Decision or the selection statement also hardly anybody makes mistake, because number 1, 2, 3, 4, draw the edges here, and 1 to 2 control can transfer, and 1 to 3 also control can transfer if the condition is false, and then from 2, if it is true, then it will transfer to 4, from 2 to 4, that we represent, and 3 to 4. So this is the representation for a selection statement, but possibly the more intriguing or confusing type of statement is a iteration statement. While a greater than b, b equal to b into a, b equal to b minus 1, and c equal to b plus d. How do we draw this? Again we number this 1, 2, 3, 4, and from 1 it can come to 2 if it is true, 2 to 3 sequence, and then 3 it needs to go to 1 to check whether the condition is true or false. So if it is true, it again executes these 3 statements and until it becomes false. So that's what we represented here, 1, 2, 3 and back to 1, and only when it becomes false it comes out to 4, and there is no edge between 3 and 4. So 1, 2, 3, 3 to 1, and finally as it becomes false comes out to 4. So that's the representation of a decision. If we know those 3 constructs, then given any program like this, do, while, if a greater than b, etc., we can easily represent that. So this is taken from The Art of Software Testing by Glenford Mayers, the same example. So please try doing this, and you should get the same control flow graph. Now how do we define a path through a program? A path is a node and edge sequence from the start node to the terminal node on the control flow graph. So we look at the control flow graph and try to find out how many node and edge sequences exist from the start node to the end node. But the problem here is that in the presence of loops, we can get infinitely many paths. Whether we traverse the loop once, twice, n times or infinite times, we can get infinitely many number of paths. So a full path testing will require too many test cases, and it's impossible actually for checking all path testing. So what normally is done to test the linearly independent paths? We define a linearly independent set of paths as those paths such that between any 2 paths in that set, there is at least one different edge which is not there in other paths. So how do we identify? Okay, for a small program you can identify what are the linearly independent paths, but complicated program, just by looking at it, it becomes very hard to identify what are the linearly independent paths. And we will use the result of the McCabe's metric, which is very easy to compute. You can compute it from the CFG, or even just by looking at the code, we can compute the McCabe's cyclometric metric. It's a very easily computable metric, and it is an upper bound on the number of linearly independent paths in a program. So it tells us that how many paths at best can be present. If we are computing it from the CFG, then one way to compute the McCabe's metric is Vg is equal to E minus n plus 2. Look at the control flow graph. Compute how many edges are there, how many nodes are there, E minus n plus 2. So that's the cyclomatic complexity, and this value tells us that how many paths at best, linearly independent paths could at best be there. What about this example which you had drawn the CFG? So how many nodes are there? 6 nodes are there. How many edges are there? To compute, we have 7 edges. So what will be the cyclomatic complexity? Is 3. 7 minus 6 plus 2. But if the graph is complex, having dozens of nodes, etc., it becomes very difficult to even compute using this formula E minus n plus 2, because you have to compute all of them. It is easy to compute using a computer program, E minus n, how many nodes are there and how many edges, and then E minus n plus 2. It's easily computed by a computer program. But if you have to visually inspect and find out how many linearly independent paths are there in a CFG, we can compute by this formula. The cyclomatic complexity is equal to the total number of bounded areas plus 1. So the number of bounded areas, this is one area and there is another bounded area here. So 2 plus 1 is equal to 3. So we can get the same answer by just visually looking at the diagram and trying to compute how many bounded areas are there, plus 1. That's the formula for the cyclomatic complexity. We will get the same result as E minus n plus 2. Okay, the visual examination can lead to 3 is the cyclomatic complexity for the same program. Now the cyclomatic complexity has many uses. One is that it identifies the number of paths. It's a measure of the number of paths. It is also a measure of many other things. For example, it is a measure of testing difficulty, because if the cyclomatic complexity of a program is 100, then we need at least 100 test cases to test it. So that's an extremely complicated code. And also it is a measure of the ultimate reliability that can be achieved here, because the more number of tests are needed, the more complex and therefore more likely to have bugs. Okay, the first one can be, we can write a simple program to find Vg based on E minus n plus 2. But then one thing we must remember is that even if we know the cyclomatic complexity is 100 of a certain program or 50, how do we know that what are these 100 paths? It just tells us about the number of paths and tells us how many test cases are needed. But then how do we know what are those test cases or what are those paths? Cyclomatic complexity does not tell any of that. It only tells us what is the minimum number of test cases required. So if that is so hard to know the paths, linearly independent paths, and also the test cases that will be required to execute those paths, how do practically path testing is carried out? Okay, here typically a programmer just enters random values. Based on his experience and judgment, he might enter values which may be random or may be guided by his knowledge of the program, and then he uses a tool, the dynamic analysis tool. The dynamic analysis tool, as the tests are executed, it keeps on showing the coverage. So the programmer keeps on giving input values until the dynamic program analyzer shows a figure of 90, 95% or something like that. Different companies have different policies of how much path coverage is required. For small programs, we can derive test cases for path testing. You can say that these 3 test cases or 4 test cases can achieve path coverage. but it is not practical for larger programs which have 50 or 100 different paths. It will take months or years for programs which have 50 or 100 paths. Just to identify what are the paths is a very difficult task. So this is just one example that for which we will have the path test cases designed, draw the control flow graph, and then find out the paths, 3 independent paths, and then identify the paths, and then find which test cases will ensure execution of that path. So for very simple programs, trivial, almost trivial programs, we can identify the test cases that are required for path testing. Larger program, it's almost impossible to identify the paths and to design the test cases. Typically, programmers keep on giving input values based on their experience, and they compute the coverage that is achieved by using some dynamic program analysis tool or a coverage analysis tool. So as we were saying, McCabe's metric is an indication of reliability, the time required for testing, etc. Not only that, it is a measure of how difficult is the program to understand. So a cyclomatic complexity is a measure of comprehensibility of a code. How easy it is to understand the program, we can get that by the cyclomatic complexity. Why is that? Why is it that the cyclomatic complexity indicates how is it to understand the code? The answer to this is that to understand a code, you have to mentally trace through the program, every path through the program. Unless you trace every path through the program, you have not understood the code, and therefore the time, the difficulty level understanding a code is proportional to the number of independent paths in the program, and that is the complexity. And because the program becomes complex, has more bugs, becomes very difficult to understand, etc., when the cyclomatic complexity number increases, many companies require that cyclomatic complexity value should be low. So if some function or a method has a cyclomatic complexity or 50 or so, the code will not be accepted. They restrict cyclomatic complexity to usually 10 or so that the code somebody can understand and maintain. So now let's look at the summary of white box testing that we discussed so far. We discussed that statement coverage is the basic testing, the weakest testing, and the strongest testing is all path coverage. But all path coverage requires too many test cases. Sometimes it is impossible, might need infinite test cases, and therefore typically we have this path coverage we mean independent path coverage, linearly independent paths or basis paths. And then subsumption hierarchy becomes this, that we cannot prove anything between a MCDC, multiple condition coverage, and the path coverage. But I was asking you to prove that linearly independent path coverage is a stronger test than branch coverage. Now let's look at another white box testing, that is data flow testing. So here the test cases are expected to cover the different definition uses of variables in a program. The definition and uses of variables in a program are covered by the test cases. So given a statement S, we can identify what are the variables that are defined there. So this is the set of all x such that x is defined in the statement S. For example, a equal to b is a statement. So a is defined in this statement. So we write def1 is the statement number, is equal to a. And uses is which are the statements that are, which are the variables that are used in S. So in this statement uses will become b, whereas in this statement a is equal to a plus b. Def2, I should have written 2 here, def2 is equal to a, and uses 2 is equal to both a and b are used here. Now based on this, we can define a concept called as a variable to be live at a statement S, statement S1, if it is defined in a previous statement S and there is a path from S to S1 not containing a definition, redefinition of X. So whatever value has been set at S, the same value is used in S1. So that is, the variable is live at S1. And based on that concept, we can define the DU chains. The definition use chain is when a variable is defined at some statement and is used as another statement and is also live at that statement. Then we call it as a DU chain. So DU chain is defined to be a variable, the statement at which it is defined and the statement at which it is used, and it is live at this statement S1. Then this forms a DU chain. So a data flow test requires every DU chain to be covered at least once. So this is the simplest data flow testing. There are many other data flow based testing techniques. We will not go into the more complex ones. Just consider the simplest data flow testing is that every DU chain is executed once. So this is the definition of variable A, and let's assume that this statement uses a variable A and there is no intervening redefinition of variable A, then this is live at this and this must get covered. So this is one example of a DU chain. Now let's look at a fault based testing. We said that mutation testing is a fault based testing and we can check whether some type of faults are being detected by the design test cases. So the idea here is that we first design the test cases using other white box test techniques, path coverage and so on. And then after the initial testing is complete, mutation testing is taken up. In mutation testing, we make small changes to the program, and these small changes are called as mutated programs, like arbitrary changes actually. So these changes are actually the cause faults. For example, we might make a int as a float, or we make a decision A greater than B, we might make it A less than B. So are our test cases good enough that they are detecting the change that we have made? So that's the idea here. We insert bugs and then check whether the test cases are detecting that. So once we make a change to a program, we call it as mutated program, and the change is called as a mutant. For example, a mutant may be to change the type of a variable. So this can be done automatically. That is one advantage of mutation testing, that we can create mutants automatically, and there are tools available for C program, Java program, etc., free publicly available tools where you can insert bugs into the program or create mutants systematically. So once we have the mutated program, we run the test cases, all the test cases, and see if some test cases are failing. If all test cases are passed, then we know that our testing is not sufficient. So each time we go on mutating the program and running all the test suite. Obviously this is not suitable for manual testing. We need a tool here which will insert the bugs, keep on inserting bugs, or create the mutated programs, and then also automatically run the test cases, maybe a capture replay type of tool. So as long as the test case detects the change, we say that the mutant is killed. Otherwise we say that the mutant could not be detected, the mutant is live, and we need to create additional test cases such that the mutant gets killed. That's the idea behind mutation testing. Now, what are the types of mutation operators or the changes that we make? Maybe we can keep on deleting one statement at a time. We may change an arithmetic operator plus into minus or plus into multiplication and so on, change the value of a constant, change data type, int into float and so on. To be able to determine what are the kind of mutation we do, we need a fault model of a program. A fault model of a program is what are the possible faults that can exist in a program, or a programmer can write a program with which types of errors. Can he, while writing the code, write a plus into minus, plus operator minus? Yes. So that's one fault. He can interchange two statements, decision, he can make a mistake and so on. So this is an example of a fault model of object-oriented program. And based on the fault model, we can define our mutation operators. Deletion of a statement, for Boolean, replacing equal with not equal and so on, replacing arithmetic, replacing a variable, ensuring the same scope, etc. Now today we are already over the time, so we'll just continue from this point, mutation testing. We'll look at the competent programmer hypothesis and coupling effect hypothesis, which are the two underlying foundations behind mutation testing. And then we see that how to have a effective mutation testing. They said that automated tools are available to carry out mutation testing. So we'll just stop at this moment. We'll continue from this point, and the next class, please raise any questions that you might have. Please do the quizzes and also raise any questions that you might have, or if some quizzes could not be done. So till that time, we'll just stop here. Thank you.